Yeah, good afternoon, everybody. Hopefully you guys all enjoyed a good lunch. I know this is a tough spot to fill. Like you're probably still recovering from the delicious lunch we had. But today, hopefully our content would be useful to go through with you together. So today I'm joined by my colleague here, Jonathan, who's also very young and much smarter than me. So hopefully we can deliver some, we can go through some good content together. Before we start, I want to ask everybody a question, like how many of you are Coinbase users? Raise your hand. Okay. How many of you have bought, I assume that you all bought like a BTC on exchange, right? On the Coinbase Exchange? Yeah? Good. Yeah, so the exchange at Coinbase, Coinbase basically started as an exchange, right? So by every metrics, our exchange system is very successful. I would say, either you measure it by business performance or system performance. Yeah, we will keep adding it, and it's provided the revenue for us to be able to attend here and talk about all the good work that we've done. Right, so I took a look on CoinMarketCap yesterday. I think our 24-hour trading volume is 1.5 billion. So that's a lot of money. Right, so it's great. I guess today, the content we have today is basically, we hopefully can give you a general overview of architecture of the Coinbase Exchange. And then we will talk about what the state of our system can do and all the tuning that make it behind the scene to make it does what it does. But then we will go into the learnings. How do we apply the the learnings from setting up the new system to improve the old legacy system? So even though this is only for Coinbase Exchange, I hope the content we have here today can generalize and apply to many other systems as well. So yeah, so we will get started. Well, the first thing I learned when joining Coinbase or joining any other places is most users shouldn't be actually using Exchange directly, at least, right? So, usually we consider Coinbase.com as a single site or single service, but Exchange itself is actually sort of an infrastructure piece within Coinbase.com. So most people, when you buy BTC directly on Coinbase.com, you actually go through some sort of brokerage product that basically is acting as a proxy, or they usually have their own ledger system or their inventory system to actually connect to the exchange. For exchange itself, usually the only people connect to us, it's market makers and high-frequency trading systems, basically bots, and then occasionally some users also can actually connect to us. So the exchange itself basically have like a set of API, and then the amount of data we serve is actually very big. It's all about market data. So being a crypto exchange, one of the things we're very, very proud of is, first of all, we have open access. Like anybody can connect to Coinbase Exchange, but try doing that with Nasdaq, right? So it's you can imagine it's probably a little bit harder. But also with market data, like you can get full raw market data directly from Coinbase Exchange, and that's actually pretty valuable for if you want to do, I don't know, either trading or if you want to understand how crypto market function. So zooming in a little bit, right? So what's actually happening within the exchange is usually there's only two big parts that happens in the exchange. One is we call it OMS, basically order management system. The other side is usually separate. It's called a matching engine. So the OMS is responsible for keeping track of user balances, keeping does like risk checks. If support a margin, it will does like a margin liquidation, make decisions based on like how many. What's the current price of the asset, what's your balance, that type of stuff. The matching engine specifically is isolated to only handle order books. So order book, it's basically, you can imagine everybody submit orders, like basically, it's like a little bit like an auction, right? You submit the order to say, I want to buy BTC at this price, and that order will rest on the order book. And if somebody submit a sell order that basically match your price, the matching engine will basically execute the order on both sides. Right? So after that, it's going to generate market data. And you can consume that market data to make more decisions and send more orders. You can also use the fixed API or HTTP API to either place the order, cancel the order. So that's the general idea, right? So you can imagine there's definitely some hot paths, there's some warm paths, and there's like auxiliary paths that basically is critical to the function of the exchange. For hot paths, you have to, every single order need to be check the balance. You can't allow people to place orders with no money to back it up, right? So that's critical. Second is obviously the order execution or the matching itself. But then the settlement, after the order was executed, money changes hand. You have to credit the buyer. You have to debit the seller, or the other way around, sorry. But then if you don't do that fast enough, you're gonna hold other people's money at hostage, right? So that's also very bad. And a lot of trading firms, if the money was dried up, they wouldn't be able to place new orders, and the whole market shut down. And the third one, obviously, the market data feed is also very critical, because if you don't know what's going on, why would you place orders, right? Like so it's very important for like a timely delivery of the market data to the trading firms and to the market makers. So zooming in a little bit more. So what's happening within, so this is sort of like a great simplification of what trading system actually does, right? So on one side, you have a lot of orders coming in. Some orders, so basically it's all equal, right? So you have to, they all arrive on different intervals, and maybe they arrive together, it doesn't really matter. But after the trading system, usually it's separated by markets. So for example, if you want to buy BTC, use USD, then that order is totally separate from like ETH USD orders, right? So usually within the one single market, here as like trading system process is basically serialized. So in a sense, every single market is one process that basically processing orders at a very fast pace, and you can't really do like anything parallelization. You can't reorder the event. There's nothing you can do about that. But then you have the chance of actually separating all the different markets. After the order was executed or canceled, whatever, you can generate a bunch of trade events. So I think we'll get down into a little bit more when we talk about the state of art, which is Coinbase Derivative Exchange. This is launched, I think last year, right? A little bit late last year. So this is based on an entirely new architecture, and Jonathan here will walk you through on the details of it.
All right, thank you. So a little bit about me. I joined Coinbase from an acquisition of a startup called FairX. At FairX, we built a regulated futures exchange from scratch, designed to be performant and reliable. So in starting out building out our exchange, where do we even start? Well, we can start at the core of our exchange, which is the matching logic. And we can realize that it's actually pretty simple. All you have to do is handle submitting orders, match them against orders that have not filled yet, and generate fill and order events out and send them out. So being a regulated exchange, our books are public, which means that every order is matchable. There's no complex trading relationships where only certain parties can trade with others, so that greatly simplifies our programming model. As for all the other logic in our system, such as timers, admin requests, and state, that affects the trading logic. So we want to sort of sequence them with all our other events to keep it deterministic, and therefore the trading system becomes a sequencer as well. And we wanted to keep this all in a single thread. So naturally, a mental model we can have for our trading system is to treat it as a deterministic state machine. We're given an initial state plus an input. It always results in a resulting state and an output. And at any time, you can snapshot the trading system, state to a file. You can restore from that file to have a live trading system. And additionally, you can replay from an old snapshot plus some old input to catch up to the live system. So here in the bottom right, the top and the bottom are going to be equivalent. However, that requires your system to be completely deterministic, and that's easier said than done. There's many pitfalls you can have, such as data structure iteration. For example, if you want to snapshot and restore, but your data structures have resized before you're snapshotting, and when you're restoring it's back to its original size, right? The iteration might not be the same. So you don't want to use stuff like cache sets or hash maps, and we use our own third-party or our own data structures. We don't have randomness, of course. If you want to use a pseudo-random, then you need to store your seed as snapshotted state. But the big thing is behavior changes, right? You want to make changes to your code. You want to fix bugs, add features. But you need to maintain the invariant that old input results in old behavior. And what that means is that you need to gate your behavior changes on what we call feature flags. These feature flags come in as an admin request through the front door of the trading system. And these feature flag states get snapshotted into our trading system state. So given we have a state machine, we can also have a replicated state machine and put a consensus algorithm on top of it to give us high availability and fault tolerance. So here, if the leader fails due to a hardware failure or something, the other two nodes can hold a re-election, choose a leader, and continue processing messages normally. So at FairX, we use a high-performance RAFT implementation called Aeron Cluster. With Aeron Cluster, the consensus is going to be batch and pipeline with our application. So effectively, the entire system throughput is going to scale inversely with the application processing time. As per the RAFT protocol, we have to persist our RAFT log. And Aeron Archive provides an API for us to replicate this RAFT log downstream for backup. And we can do a lot of things with a replicated RAFT log. For example, we can upload it to S3. We can replay it to do some logging. But most importantly, we can use it for debugging. So we can download our prod logs to our local machine, run it against a version of the trading system that's the same code as prod, and reproduce exactly what happened. We can run it through a debugger, add some log lines, and that's extremely powerful. Additionally, we can backfill missing events. For example, if your database writer is missing some entries because it went down for some amount of time, we can generate those DB entries locally and copy them onto the production server. And also, we can integrate it with our testing frameworks. We can have it part of our CI/CD to avoid regressions. Another thing is that we can replicate it downstream to replay. So since our system is perfectly deterministic, all we need to do is replicate our input rather than our output. And the benefit of that is that our output is most times larger than our input, and at the same time unbounded. So one order that's coming in can cause a potentially cascading set of events, like multiple fills or cascading stop order triggers. So replicating our input gives us more deterministic network bandwidth usage. So in this diagram here, we replicate our RAFT log downstream to an Aeron archive. We have a trading system run on that machine to replay the RAFT log, record trading events, and any service on that machine can replay those trading events via shared memory. We can extend this even further for scalability. Let's say you wanted to shard your services. If we have a binary tree level model of replication where each node replicates at most 2 other nodes, then that means that the latency from a given node to the live system scales with log n of the number of nodes in this graph. And additionally, your bandwidth usage is going to be bound by a constant factor. So zooming out a little, this is what the entire hot path looks like for a system. We have an order submit from a client going through an order gateway, being parsed and validated, and sent as a request to the trading system. The trading system is going to do consensus, and once it gets quorum, it's going to run through the matching algorithm, generate any fills or order events, send it back to the order gateway to be translated via whatever protocol is being used, and send back a order act to the client. So at FairX, we've been able to achieve round-trip time outliers less than 100 microseconds, medians less than 50 microseconds. Our trading system processing times are pretty fast, given that matching is pretty simple. So it's around 1 microsecond. And with load testing, we've been able to achieve 300,000 requests per second peak throughput. And this is what our hardware environment looks like. We are co-located in a data center with our customers because we are fast and network latency matters. We run on commodity hardware with very fast disks. So we use Intel Optane drives that are faster than enterprise SSDs. That means we can f-sync our RAFT log if we need to without too much penalty. We use very fast switches, so 350 nanosecond cut-through forwarding switches, as well as switches that support real-time packet capture without any latency hit. And also, we isolate our NICs for low latency and bulk traffic, which means only the order flow traffic only goes through one path, while our replication goes through another path. So I'll hand it back to Yucong to talk about on the AWS side.
Yeah, so how did everybody feel? Like 1 microseconds, that's pretty impressive, right? And we had another project that basically tried to replicate this, set this up on AWS Cloud. And you can imagine the first iteration sucks. Right, so it was very slow. It was, people question, oh, you already have this working in the data center. Why do you even bother, right? Well, I mean, I'm kind of preaching to the choir here, like the benefit of the cloud. But then there's also this mandate, right? Like we have to make this work on AWS Cloud. So then, well, besides codification, besides collaboration you get from migrating to a cloud, I think the biggest benefit we get is the personal dev environment. You can basically spun up the entire exchange nilly-willy, right? Like you can, I think we're running like tens or dozens of environment every single day, test all the features, all the PRs, then you can do like CI testing directly on your own personal environment, replicate, test directly with replication of a version of the product log or whatever you want to test with. So scale a lot better than buying hardware ahead of time and deploying everything. But then the challenges we definitely run into, right? Like first of all, AWS doesn't actually control what hardware do we use. And we do actually use a lot of customized hardware, pick them very specifically for achieving the performance that we do. But then secondly, it's about toolchain, right? Like DC, AWS, we have to be able to maintain both. We are not going to migrate the production system to AWS because that's under-regulated and it's actually required to maintain the current infrastructure unless you want to deal with CFTC to make a change. So the first thing the first challenge that we run into is obviously with compute and storage, right? On AWS, you don't get to say what machine you have. You just say which family it is, and actually took us a little while to understand what's the difference between all these machine families, and we end up picking Z as the one that in charge. But I wouldn't go too much into why it's best. But I put a link here, like this website. It's going to help you on understanding a little bit on that. But then we also need some help within the AWS to understand what does Z machine actually, what kind of feature does it have? Does it have like so Z machines basically have like a higher frequency, the highest single-threaded performance than any other machine family. And but then you come with capacity restraints, and you have to satisfy a bunch of different parameters to make sure it actually works for our case. Then the storage side, you have I think by default the choice is EBS, but EBS is a distributed block storage. So your storage is never on the same machine as you. When you write, when you do f-sync, it's going to be like painfully slow. But then the only other choice is instant storage, which is a local NVMe disk that actually connect to the AWS. So yeah, so I guess the point I was making here is that if you can still get pretty close performance on AWS, but you just have to understand how AWS data center, how AWS hardware was actually set up to actually achieve that. So the second challenge that we ran into is obviously the networking. So you see, Jonathan was talking about we're able to have 1 microseconds processing time for an application. So what that means is, just to making sure everybody understands, 1 microseconds, there's like 1,000 microseconds within 1 millisecond, and there's 1,000 milliseconds in 1 second. So what it means is the network latency is actually dominating factor in the entire pipeline. So basically you spend more time waiting for your switches than waiting for the code that we actually wrote. So this is unfortunate, but I mean, it's the fact, right? So the first thing you learn on searching like a latency on switches or network latency is that you end up on having here, like basically there's two kind of switches on the market right now. There's one that you don't use, which is pass-through. There's one that everybody else uses, which is a store and the forwarding node. So basically they read from the buffer from one port, store into its internal buffer, and then make a decision, and then send it to another port. So that's going to cost you about 5 microseconds to 50 microseconds, depending on how much money you actually spent. But then there's a pass-through forwarding switches that basically does the streaming, which has a very low latency, right? So again, on AWS, you sort of, in order to actually get good performance. So first of all, AWS doesn't, I don't think they use pass-through switches, and they're not going to add new pass-through switches just for us, right? So we have to deal with the store and the forwarding switches. But even then, you have to understand how AWS internal network is set up to be able to get a good performance numbers here. So we all know there's regions, there's AZs, but do you know there's sub-AZs? And do you know AWS Network has this architecture called spine and leaf, right? So instead of having everything, every Tor switches, every top of a rack switches connecting to each other, which cannot scale, they usually set up a spine, which is like a bunch of really big aggregation switches, and then connect them directly to each other. Then you have like a bunch of leaf switches that's connected directly to one of the spine. So in order to, you can imagine like in order to get good network latency numbers, you have to be on the same spine block or leaf block that to be able to talk within the rack, or maybe just one rack apart, right? So yeah, you have to understand region, AZ, sub-AZ, and then you have to decide whether you want to all be on one rack or you don't want to be on one rack. But then again, you have to play with the storage and compute requirement that you have, because you can't just have like one machine. If that's the case, then it's much easier, like everything happens inside that box. But you have like a couple machines that need to be close together. So you have to use a feature called customer placement group. Then you have to deal with the capacity reservations, because it's very hard to have a big cluster placement group. You can imagine if on a public cloud, everybody is trying to reserve their own instance, and it's very hard to get the star line to give you a perfect placement of your machines. So even if you use all of that, you're still going to have like issues where some machines just slow, right? For whatever reason, maybe the cable was loose, right? So you just have to actually verify and test every single machine you get, and then you root out the bad apples. So on the right side, so this is like they don't talk about it. Every time you ask AWS guys, they say, oh, you should just treat US East 1 as a single region, and if you want to failover, get 2 AZs. But then what they don't tell you is between 2 AZs, they actually have like incur about a millisecond latency to 1 millisecond to 2 milliseconds. So imagine that in our case, we definitely need to be within 1 AZ. But the question is then which AZ do you want, right? So this is somebody did the work to measuring all the inter-region, inter-AZ latencies, and you can see there's like in the older region like US East 1, you have a very complex topology that you have to actually go through and test it to make sure that, oh, you want 2 AZs, but you don't want them to be too far away, and then you have to again play with your storage and the compute constraint to get the machine placement you want. Yeah, and then specific to AWS, the AZ number you got, like US East 1A, is only for you. That it's get mapped into some sort of a AZ ID that's shuffled across all the different user accounts. So basically, yeah, just pay attention to that. Like when you optimize for this account, it's not going to be optimized for the other account if you have multiple accounts. So coming back to this, right? So on data center, you remember in a couple slides back. So basically, what we have on AWS is we actually have similar performance on training system. We can still do like 1 microseconds because the CPU, all the training that we did. But then we paid more price on network hops. Also because we new design, new architecture, so we end up requiring more hops across switches. You see the dominant factor here is still network. And if you ask AWS, they say, yeah, like everybody ran into this problem, and they're working for solutions. OK, so hope everybody is having fun. So I'm going to hand over back to Jonathan to talk a little bit about system level, application level tuning we have to do for the real low processing latencies.
Thank you. So in our trading system, we want our memory access to be very fast. And given the ordinality of data that we work with, so like tens on hundreds of objects in a data structure, cache locality is going to outweigh the benefits of big O notation. So a lot of the time, we use arrays and iterate over them, or nested arrays. We use primitive-friendly data structures. It might be a Java-specific thing, but when you want to insert an integer or a long into a map, it's going to do something called boxing, where it wraps the primitive in an object, and that's going to allocate, which is not what we want. We deserialize our memory directly into primitives instead of copying any buffers over. In a trading system, we have no use for strings. Right? All it's used for is pass through back to the client, so we encode them as 2 longs, and you can fit them into 128 bits depending on your character set. And also, we do no allocation on the hot path. For any objects we do create, we try to reuse them. We also have very small messages. So we use an encoding called simple binary encoding. It was meant for fast financial messages, but we also use it internally. Byte alignment matters with these messages. So generally, you want to sort your fields such that the 64-bit integers are first, followed by 32-bit integers, followed by shorts, enums, var data, and bit sets. And the reason for this is for deserialization, especially for market makers who are using FPGAs. If we need to add fields to the end to be backwards compatible, then we might add padding if necessary to enforce this byte alignment. And in our exchange, we use Java. The reason for that was simply because we all knew it. And at the same time, our Aeron cluster library is written in Java, so the client is implemented in Java. And a big problem with Java is Warmup. So when you first run a program, it's all going to be bytecode, and it's all going to be interpreted. Therefore, it's going to be slow. But you can warm up your code by running orders through it. However, since we're a regulated exchange, we can't do that. We can't run a market maker against our own code. Otherwise, we'll get in trouble. So it takes around 10,000 invocations of a function for the JIT to compile our code. So we have a solution for this. It's using Azul Zulu Prime. It's a proprietary JVM that offers a feature where you can run your code elsewhere, run it against some input, and it will generate a JIT profile for you, plus any optimizations, such as branch predictions, so that when you deploy and load up this profile onto prod, then your first orders will be fast, and it will remove any jitter that's generated from JIT compilation. A second big factor is garbage collection. So with open source JDKs, you're going to have stop the world events where all applications are going to have to freeze until GC finishes. And that's jitter that's intolerable for an exchange. So Zulu Prime also offers a pauseless garbage collector, so we don't have to worry about GC at all. As for network optimizations, our servers are in a data center, so that has multicast support. We can use multicast for 2 different things. First, the consensus algorithm. When a leader sends a consensus message to 4 of its followers, instead of sending 4 packets, it can send just 1. And we send our output to our latency-sensitive services as well. Our messaging and middleware is based off of Aeron. It's high-performance messaging, implementing reliable transport over UDP. You can modify some settings to implement congestion control and flow control. To optimize for throughput, you can set your socket buffer sizes so that the amount of data in flight on the network is equal to the bandwidth delay product between 2 machines. And you can set your MTU sizes higher, up to 9K, to have more natural batching for throughput. Additionally, we use kernel bypass. So when a packet goes through the Linux networking stack, it has many steps to go. and it might be jittered by whatever queues in that workflow. So instead, our application is going to pull packets directly from the network interface card and send directly to the network interface card. So in a data center, we use a library called OpenOnload that works with Solarflare NICs. And on AWS, we can use something called DBDK, which Aaron has native support for, although it's a premium feature. And on the right side, you can see what the numbers look like running an Aaron point-to-point test, sending as fast as possible. With non-DBDK, our numbers are 38 micros versus 28 micros. Our max is improved from 1.8 milliseconds to 500 micros, and our throughput improves from 80 megabytes per second to 500 megabytes a second. But even with all that, you can still have spikes. And this was me a few weeks before launch. In this case, it's because we forgot to turn off swap. And the question you have to ask yourself is, knowing that your application is fast and your network is fast, does your application and your hot threads have all the CPU time that they can get? And you can check this out with various methods. Using proc schedule debug, you can see within the CPU what tasks are running and how much runtime they get. You can go into schedule stat to see for a particular thread how much time is spent on CPU, the run queue, and the time slices on the CPU. Ideally, you don't want the time on run queue to change because that implies it's being context switched. You can look at the interrupts and soft interrupts running per core. And if you want to get even deeper, you can use perf or BPF tools to see exactly what might be contributing to latency on your system. So my recommendation to have a holistic view of the system is NetData. It provides a very nice web UI where you can see per CPU interrupts, soft interrupts utilization over time, as well as other stats about your system, network, memory, disks, and file systems, so you can spot out any obvious red flags. So some tips to improve giving your hot threads as much CPU time as they can get. The first one is you want to pin your hot threads to hard-coded CPUs. And the reason for that is it helps prevent context switching, and it prevents cache misses, especially particularly L1 and L2 cache misses. You can do that using taskset, or you can use a library for it. We want to isolate our hot CPUs to prevent any user space threads from being scheduled on those CPUs. And additionally, we want to busy spin our hot threads, so to monopolize the CPU and to pull any buffers as fast as possible. And lastly, since isolating your CPUs might not necessarily stop the kernel from running stuff on it, you want to set affinities to your hardware interrupts, your kernel work queues. You can do this using Tuna or setting it manually on the file system. Additionally, there's some kernel parameters you can use to prevent soft interrupt requests from running on those cores, such as RCU no callbacks or no hertz full for local timer ticks. And other tuning that you can do is, first off, paying attention to your CPU layout. So if you have two CPU sockets, only one of them is going to be close to your network interface card. And what that means is that you want to pin your hot threads to those CPUs and lock your memory to that specific NUMA node. And additionally, you want to either turn hyperthreading off or isolate the corresponding CPU, because if there's another application running on the corresponding logical thread for a CPU, that means you have effectively half the L1 and L2 cache. So I'll hand it back to you, Song, to talk about the legacy system at Coinbase.
Yeah, did everybody remember what was shown on the slide? I can take some quiz. No? Don't worry, yeah. So I know we flipped a lot of content there, but we're going to publish the slide anyway, right? So you can read it offline, and then you can grab us in the hallway to talk about it. So the intention for us is always to give you some tool set so that you know what's available to tune your performance. But then you also, what I want to do next is to set you some expectations on what level of tuning, or if you want to make your system fast, which one, how much effect, and which one what methodology you might took to actually do that. Right. So I joined Coinbase a year ago, and imagine like a Coinbase was started in 2015. Internal system were continuously developed, and then multiple system was rewritten, and now we're in this microservice world where, familiar names, but you don't know what it does, right? So this is likely the first problem you run into, same as me, trying to optimize a legacy system is trying to figure out, what our life, all the hot passes actually involves, right? So this is actually dating back from me being a Google SRE early days. The most useful thing I learned there is like you have to do this life of a request type of thing. So you basically trace it all the way from the client to through internal systems, and then goes back to the client to understand what actually takes for the request to finish. Then this is what you usually does. It's you want to start creating a different dashboard. Usually you create a component level dashboard. It's focusing on the service and service internals. But then for end-to-end latency debugging, you want to create some sort of like a flame graph. Essentially, you start with the end-to-end latency, but then you get into what exactly contributed to that latency throughout the system, and then you generate a layout just like this, right? So graph everything, right? Even though you have all the graph already, it's much easier to have a single dashboard that basically shows you. But don't forget to put this thing on top to make sure everybody knows how to read this as well. A couple things here is one, you always want a client-side view versus a server-side view, because you don't know what happens when a client sends a request and what's involved in the middle, and then server-side, how long does it take to actually process it. So we run into some surprises about, for example, info inefficiencies, like AWS load balancers just add 1 millisecond to every request it gives. Right, so you can't discover that unless you start to pay attention to client-side view metrics and server-side metrics. Second is your end-to-end latency request. End-to-end latency is very different than if you measure the per unit amount of time that it actually took. The reason for that is there's a reordering, randomization happens within the application. So usually, you want to imagine the box, servers are boxes that basically has like an input and output, and it's all first in, first out, but it never works out that way. So your end-to-end latency is higher if you just took how much, how long does it take to process each messages and then divide it by 1. Then the other thing is if you use tracing, you have to be aware of the sampling. The sampling logic usually only keep the slow ones and drop the fast ones, so it's not uniform. So your dashboard may be completely screwed based on how many traces, how many requests you have, right? So then when you get to the bottom of it, you want to differentiate happy paths versus unhappy paths. Happy path is basically everything is aligned, everything is working as fast as it could, but then you still have some fixed overhead you have to fix to get those numbers down, right? So for example, I talk about load balancers and then cross AZ traffic, right? Like the legacy system is not deployed in the single AZ as we designed for the new system, so we have to fix that. Otherwise, you incur like 1 millisecond latency on every single request. Then it goes down to the application code itself, right? So the old legacy system is written in Golang, which is a little bit different than Java does. So some good, some bad. The good thing is it doesn't have this warmup issue because it's fully compiled to native code. But then you also have the same issue with allocations. You also have the library that you use that may incur a lot of overhead simply by observing the system. So in a sense, legacy system is like a Heisenberg system, right? Like you cannot know what's going on if you collect you will affect the latency if you collect too much data, but if you don't collect enough data, you don't know what's going on, right? So yeah, this is an example. Like I put this diagram out. So the top part is the new system, how abstractly what the logic actually involves. So you can see we found like so there's only one RAFT round that basically only the trading logic and balance check all happen within this single RAFT round, and this RAFT round is configured now to do fsyncs. But then we have the graph that's basically drawn similarly to what a new system does. But on the old system, you can see like we do balance check, which talks to the DB, but then we also have a RAFT over there. And then we found out, oh, are we actually doing fsync over there? And why is that? Like fsync basically adds a milliseconds, half millisecond latency to the every single request. So this is type of issue that you found when you try to optimize P50s, happy passes. Then I won't go into too much detail about this, but you have to know in Golang, when writing Golang code, you have pointers, but those are not your C++ pointers. So don't think it's more efficient. It's actually maybe worse by passing by value. So I mean, I have the link here. You can read about it, but usually it has if you just copy a small struct, it may be like 8 times faster if you do it passing by a pointer, which make it onto the heap, and then GC had to scan it, and then everything else, right? So that's another thing. Okay, so unhappy pass. Unhappy pass is P99 and max, right? So we had an issue where P99 is like way off in the millisecond range, and even the max is like 300 milliseconds. What's going on, right? So this is where you start to look into scheduling delays, non-FIFO behavior of your system, and initially I thought it was GC. I was like, maybe they use the prime Java JVM. It's so awesome that it doesn't have GC issues, and Golang has EGC issues. But then while dig deeper, you actually found out Golang doesn't even have a GC issue at all either. So basically, I think after Go 0.8 or 9, you basically have like only 200 microsecond delay on every single GC. So that's not the issue. But then I try to use a profiler to sort of monitor our internal system. This is sort of a screenshot that you can, the kind of data that you can get from the running system. So one thing I noticed here is we have like 34,000 Goroutines happening here, right? So what's that? I mean, if this is C++, you will find out, oh, you can't have that many threads. It's going to trash your system and make latency slow down, right? So then Golang profiler basically points you, in the corner that you have a scheduler delay. What does that mean, right? So this is what we're going to go through a little bit in depth here. So basically, in Golang, you don't have thread, but you have Goroutines, right? Goroutines are not your thread, but they are actually, there's a Golang scheduler that basically schedules Goroutines to run on each individual thread. By default, Golang only launch the same amount of thread, which is represented at the green circle there, to actually run your Goroutines. So each one have like a local run queue, and then your Goroutine was scheduled on top of it, and then they process it one by one, right? And then there's also a global run queue where if the local run queue is full, you get it put into the global run queue, and then who knows what Golang scheduler decide which CPU you're on to actually execute this. To visualize this a little bit better, I took one system and try to, so this is my invention, like I try to sort of visualize how this application actually works, handling requests. So on the left side, it's the client, and each arrow is like a single, imagine that as a lane of the highway. And each car here represents a Goroutine, right? So in the middle, the small boxes, that's the Golang channels. So basically what this application does is there's a Goroutine pulling data out of the TCP connection and then put them into a Golang channel. And then we have one single Golang channel, one single Goroutine that associated with each channel to actually go pull the data out and then submit it to the gRPC channel and send it out. So you can imagine the problem here, right? So you have so many cars, but you only have like, 16 drivers. So imagine the drivers going into one of the cars, drive a little bit, finish the task, and then immediately switch to another car randomly around the picture here, and then do that work. So what you end up get is it's definitely not FIFO behavior, right? So it's like a big randomization on the order of orders that you actually processed. So then there's another system which is a little bit different. So instead of having like internal queues, it has this DB to talk to. So talking to a DB involves getting a connection from the pool, talk to a DB, wait for the response, and then goes back. So again, the car here that basically they go to one of the DB, DB connections and then do the work and then come back. And then by the time it come back, there may be a lot of more requests has already went through it and actually does that. So again, randomizations. Then we have our bias-tuned performance system that called trading engine that actually perform a little bit better. So what it does is it has like internal channels and a single Goroutine basically pass one message from one channel to another. So you can imagine the problem here is gRPC. When you're using unary request mode, actually generate one Goroutine per channel, per request. So again, you have this big issue of you don't have enough drivers, and basically all the internal processing stuff is being stopped by there. So again, I won't go too much detail here, but two mitigations. One is you can spin your Golang code. So basically, instead of giving up CPU, just basic spinning. Second is you can batch. When you use channels, you need to batch. Like I think this will apply to any sort of Go programs. Well, the big conclusion here is Golang is really not optimized for throughput. But again, nothing on Linux is really optimized for throughput. For latency, it's all for throughput. Actually, that's usually what you want. Yeah, so the fsyncs is also, again, an issue. So after everything, we were like thinking why the old system was just slow, right? Then we realized, talking to a DB it's not really that difference between doing a RAFT round, right? So what happened here is really just we're doing fsyncs on every single request on DB because that's what Postgres does. But on the first graph, you basically don't do that. So I guess that leads to my conclusion of my presentation. Sorry about dragging a little bit longer. But I think Elon Musk basically have a pretty famous quote saying, the big error of a smart engineer is to optimize something that should not exist in the first place. So I was hoping this will be useful to you, and thanks again for coming to our talk, and happy to chat and follow up. Thank you.